who worked on slow-mo, which was downclocking Wi-Fi. So to atone for his sins, he's going to talk about CQIC, which is about improving performance over cellular networks.
Thanks for the intro. Good afternoon. So this is a joint work with my colleagues, Hao, Anku, and Andreas from Google, as well as my PhD advisors, Jeff and Alex from UC San Diego. Mobile data is growing at an explosive rate, mainly driven by applications like video streaming and etc. As a result, mobile carriers have spent a tremendous amount of money to cope up with that demand. Of course, they want the money to be well paid off, but that largely depends on TCP's performance in cellular networks. Why? Because TCP is still a dominant transport protocol for data delivery in cellular networks. We know TCP works great in the wired domain. However, it doesn't really play well on the cellular link. This poor protocol interaction leads to problems like resource underutilization. In some cases, more than 50% of bandwidth could be wasted. It also translates to bad user quality experience. You got large RTT as well as lots of packet losses. So the fundamental reason is that TCP is unable to catch up with the fast-changing channel dynamics. So what are we going to do about that? Well, we could open up the layers and pass the information about the cellular link all the way up to the TCP congestion control engine, which is also known as cross-layer approaches. There are many, many great pieces of work in this domain. In fact, we just heard one in the previous talk. So here, I'm just picking a few representative ones. Some efforts try to conceal the non-congestive events by retransmitting packets in the last hop, or masking away spurious timeouts due to handover. Others have built various models to predict the bandwidth, which helps TCP to do a better job. In general, we observe that a lot of such work try to split the connection into two parts, or at least the management into two parts. We let TCP to handle the wide segment, and we came out with a lot of interesting mechanisms to handle the cellular link. So in CQIC, we try to rethink about this split connection or split management design choice, and explore the possibility of having a single management plane that controls the entire end-to-end connection in cellular networks. We are primarily motivated by the following. Well, a significant fraction of mobile traffic comes from applications like video streaming, software updates, software downloads, and more often, such flows are typically served by CDN or content delivery networks. To improve user PoE, CDN operators like Google, Akamai have pushed very hard to place servers inside a carrier's network. As a result, the average hop distance between client and server is now much, much reduced. It is often the case that the last hop is the bottleneck link. Interestingly, we also noticed that the newer cellular technologies like HSPA+, LTE, LTE Advanced, tell us way more about the last hop capacity. I will come to that shortly, but before that, I want to give you a high-level overview of CQIC. So this is an animation to show that they actually push server from the general internet backbone all the way to the core network of mobile SP. Before that, I want to make it very clear that the initial focus of CQIC is emphasized on a subset of flows that are bottlenecked by the last hop. It also happens that this subset of flows also constitute a significant portion of mobile traffic. The high-level idea of CQIC is really straightforward. So on the client side or the mobile phone side, we extract capacity information from the rich physical layer messaging being exchanged between the mobile phone and the base station. We then feed that capacity information directly to the server And the server would react and adjust its packet sending behavior based on the received capacity. Now let me walk you through how the client actually extracts the cellular capacity information from the physical layer messaging. In addition to data flow, there are many control messagings being exchanged actually at the same time between mobile phone with the UE and the base station with a node B. So here's a concrete example on what's happening on the downlink for HSPA Plus network. LTE has similar procedure. So the first step, the UE reports on the channel quality. That channel quality is summarized as a single crisp number known as channel quality index, or CQI for short. After collecting all the CQI values, node B needs to decide two things. One, which subset of UEs do I want to serve? Two, at which data rate? And then broadcasts such decision, and followed by the actual data transfer. And finally, UE sends back acknowledgements. So how does a base station actually determines at which data rate should I serve this UE? It turns out that 3GPP actually recommends the following CQI to read mapping. For example, if the CQI value is 15, then the UE should be served at 1.66 megabits per second. Well, because this is only like a recommendation, different base station vendors may choose to implement their own mapping. So we want to understand how much variability are out there due to implementation. In this experiment, we profiled about 24 base stations scattered throughout San Diego. In the graph, the right line shows the spec, and each black dot represents a CQI to read mapping we profiled for some base station. Well, as we expected, yes, there are some variations. But good thing is that the variation isn't too much. In other words, the actual implementation isn't too far away from the spec. Perhaps a more important question here is that, let's say even we know that it doesn't matter as long as we have a CQI to read mapping for some base station. Another question is whether that mapping relation is going to persist throughout the day with different mobility pattern. So we repeat the same experiment by fixing a particular base station. We then vary, we then do the profiling again at a different time of the day, try to simulate different cell load. In addition, we create different mobility patterns. It turns out that such mapping is rather consistent. There's little variation across the day, across different mobility patterns. So it is this stable mapping that allows us to actually do capacity estimation based on CQI values. So sounds like an easy task, so we just plug in the CQI value and they give you the capacity information. But if you look at the graph, there's a large discrepancy between the actual rate, which is the blue line, and the estimated rate, which is the black line. We then realized that, oh yes, because there could be many active UEs in the same network, and it somehow runs out, it somehow exhausts available channel resource. So those UEs need to share the channel resources with each other. Essentially, you need to have this time sharing. So in cellular space, we have this notion of discontinuous transmission or discontinuous reception, which essentially summarizes the amount of time sharing. So our new estimation algorithm incorporates both CQI as well as DTX information. And the final estimate is shown as the pink line in the graph. As you can see, it's very close to the actual rate right now. We want to comprehensively evaluate the prediction accuracy. So we repeat the same, we repeat the experiment across 24 base stations. Overall, the estimation method is both, our estimation method is both accurate as well as precise. The mean estimation error is about 8%. The 80 percentile error is less than 20%. So far I have discussed how we extract capacity information directly from physical layer messaging at the client side. Now I'm going to talk about how the server is going to react to that capacity data. Ideally, it should be a simple task. You give me a capacity data, the server is just going to paste out the data, the pace out the data packets according to the received capacity information. But sometimes because we could have estimation errors, so we don't want to blast a lot of packets in the network and end up create a lot of losses. So instead, we combine both read-based as well as window-based congestion control. We keep track of the total unacknowledgement bytes. If that's smaller than a predetermined threshold, we're going to stay in pacing mode. Otherwise, we switch to window-based mode. There's a little bit more detail on our implementation. So we implement CQIC as a new congestion control variant in Google's QUIC framework. For some of you who are not quite familiar with QUIC, so QUIC is a UDP congestion control protocol developed by Google. We make use of Qualcomm's QXDM software to extract both CQI and DTX information from the radio at millisecond timescale. We then set up the following experiment to compare the performance of CQIC and TSP in terms of throughput and RTT. We place the server inside the core network of the mobile carrier to simulate a typical CDN scenario. We vary the flow size from 0.1 to 20 megabytes so that we can comprehensively evaluate the benefits of CQIC. So let me present the results for study case first. The x-axis shows the flow size, the y-axis shows either the throughput or RTT. As you can see that because CQIC doesn't need to go through slow start, so when for small flows, such as like 0.1 or 0.5 megabytes, it's able to improve the RTT by a factor of 1.5 to 2.8 compared to TSP. As you can imagine that as the flow size increases, the slow start effect starts to fade away, and eventually TSP tops the performance of CQIC. However, if you look at, for large flow, if you look at RTT performance, because CQIC doesn't send additional packets to probe the bandwidth, in addition, CQIC also reacts to the changing channel condition instantaneously. It essentially eliminates the buffer blow effect. So as a result, you can reduce the RTT by a factor of 2.8 to 2.9. So here's the result for mobile cases. The trends are generally pretty similar to the study ones. I just want to point out one thing that if you look at the 20 megabytes in terms of throughput, CQIC is going to gain an additional 8 to 10% throughput compared to TSP, because this time there are more channel variation in the experiment. Like any new congestion control protocol, people is going to challenge you about, how about the fairness? We consider two cases of fairness: inter-UE fairness, which concerns about UEs in the same cell network. Also intra-UE fairness, which are the flows in the same UE. We view that the inter-UE fairness is less a concern for the following reasons. Number one, each UE has its own dedicated queue in the base station. In other words, a CQIC flow is not going to create a packet loss in a different queue that's assigned to a different UE. Also, the base station tries to implement some notion of a proportional fairness. That said, even a CQIC flow always have data to send, it is not going to hog the entire cellular link. It's a little bit tricky for intra-flow fairness. Think about how you would fairly allocate bandwidth among coexisting TSP/QUIC flows, CQUIC flows. We envision something like a connection manager might help, but we actually haven't really looked into this. I want to briefly touch a little bit on deployability. Like I said, right now the CQI and the DTX is there. They exist in your phone. It's just the case they are contained in the radio firmware. We just need to open that information up to application layers. Some of you might concern the CQI rate mapping variation across base stations. For the sake of time, I'm not going to explain in detail, but we can definitely chat on that offline. So overall, in CQIC, we try to figure out whether we can come out with a single management plane congestion control that is entirely based on last hop capacity information. We specifically targeted for a subset of flows that are bottlenecked by the last hop, which also happen to constitute a significant portion of the mobile data traffic. Our early results demonstrate there are great performance benefits. moving forward, we want to look at intra-UE fairness, also how to handle flows that are not really bottlenecked by last hop. Thank you. Also, we are also hiring, so if you are interested, come to talk to me during the workshop. Thank you.
Thank you. I'll start by asking questions, so please do line up. So a couple of years ago at MobiCon 2013, some colleagues of mine from India had built something called LoadSense, and I forget what cellular metrics they were using. I think the metrics they were using were before they even established a ready bearer connection. So I don't think they were using.
I think
do you know what they were using?
Yeah, if my memory is still fresh, I think they look at some of the power consumptions traveling for the state of the radio. Might be wrong, but I think that's just looking at some other metric to estimate the cellular capacity.
Yes, they were basically trying to estimate